Welcome to the Explainer. Today we are jumping right into a kind of digital autopsy. We're looking at a massive architectural reality right beneath our screens, the hidden mathematical collapse of our hardware. It's an obscure, microscopic quirk, but it is literally threatening the architecture of AI and our fundamental digital trust. Let's get right into it.
Okay, so let's shatter a core myth right out of the gate. If I ask you, are computers actually perfect at math, you'd probably instinctively say yes, right? We love to think of our devices as these flawless, unyielding logic machines that always calculate exact truth. But physically, down at the bare silicon metal, that is the grand computational illusion.
Take a look at this staggering number, 80 to 90%. That is the estimated percentage of modern AI compute cycles relying on hardware that is basically just guessing. When these massive large language models are doing their heavy lifting, they aren't using exact math, they're estimating. And we need to look at exactly why that happens.
Which brings us to part 1, the FPU gambler and the wood chipper effect. To really understand this, we have to shrink all the way down to the microscopic silicon level. Deep inside your device is a component called the floating point unit, or the FPU. And honestly, you can think of the FPU like a frantic gambler throwing darts blindfolded. To get the absolutely blistering speeds we need from modern computing and AI, chip manufacturers literally burn secret proprietary seed tables into the physical silicon. When the FPU hits crazy complex continuous math, it has to squeeze those infinite numbers into fixed digital slats. It does this by constantly dropping tiny fractions, a standard known as the 23rd bit chop. And because this relies on corporate secrets, an ARM chip and an Intel chip might actually give you fractionally different answers deep down in the decimals. This creates a compounding, invisible snowball of errors called non-deterministic drift.
And the real-world consequence of that drift is devastating. It's what's known as the wood chipper effect. When AI ingests exact source data, say a copyrighted book or a critical financial record, the hardware then does complex math and approximates it. Because that math was just a highly educated guess, the exact mathematical path back to the original source data is totally obliterated. It's literally like tossing fruit into a giant digital blender. You know exactly what went in, but once the FPU gambler processes it, you absolutely cannot unblend that smoothie. The chain of title is gone forever.
So we're faced with a stark hardware divide right inside the computer's brain. On one side, we've got the FPU gambler, which, as we just saw, is incredibly fast, but lossy, probabilistic, and entirely unaccountable. But on the flip side, we have our deterministic hero, the arithmetic logic unit, or the ALU surveyor. Now, the ALU surveyor deals strictly in absolute 100% exact deterministic hardware truths. It operates on a relentless metronome of clocked voltage. 1 + 1 is exactly 2, every single time on every single machine on Earth. It is a globally accountable, universal witness. To really grasp how severe the FPU's limitations are, check out this brilliant quote from researcher Kyle McLean-Smith. He points out perfectly that the current floating point paradigm is, quote, fundamentally an approximation system, not real arithmetic. You just cannot build perfect, trackable providence, or absolute digital trust, on a foundation that is actively throwing darts at a board. True forensic precision is mathematically impossible under this current system.
So let's move on to part 2, hitting the trig wall.
Now you might be wondering, why can't we just use the exact ALU surveyor for everything right now? Well, we hit the trig wall. There is this massive friction point between the fluid, continuous meaning of human associative thought and the rigid digital grids of a computer. Modern AI models use continuous vector spaces and heavy trigonometry, like cosine scoring, to map out meaning and relationships between concepts. But standard hardware fundamentally cannot process smooth, continuous geometric curves without guessing. These massive trig operations literally force the processor to rely on the FPU gambler to estimate the angles.
Which leads us to part 3, the ultimate weapon, side normalization.
This is the breakthrough. We need a revolutionary mathematical fix to completely bypass the FPU gambler and connect the fluid meaning of AI directly to the unyielding certainty of the ALU surveyor. The 1-2-3 punch here is a framework called side normalization. Step 1 is the crucial anchor. We lock the entire coordinate system to the transverse constant, forcing the variable a to always equal exactly 1. Step 2, because we are anchored to 1, we can completely replace all that heavy continuous trigonometry with simple discrete reciprocal shifts across a rational pixelated lattice. And step 3, we use global remainder tracking, or GRT. to explicitly track any leftover decimals as a strict machine state rather than just rounding them off and losing them.
Just think about the sheer impact of that for a second. By anchoring to a equals 1, side-A normalization physically turns messy, complex quantum curves into perfectly exact, straight lines. It is an absolute game changer. If you're dealing with straight, discrete lines instead of continuous angles, you completely eliminate the need for complex, power-hungry trigonometry. You have officially put the guessing FPU gambler out of a job.
Moving right into Part 4, the exact ALU surveyor takes over. With the trigonometry completely out of the picture, we can finally shift our operations away from the frantic gambler. By operating on pure integer geometric rigor in the ALU surveyor, we actually restore a fundamental physics principle to our computer systems, Noether's theorem. In physics, symmetry means perfect reversibility. Because there are 0 hidden approximations and 0 dropped bits, every single operation is mathematically symmetrical. We can work backward, forensically tracing every single digital step on a mathematically absolute path. The original data provenance is perfectly preserved. The AI smoothie can actually be unblended. We achieve what the sources call absolute, strictly unbiased, bit-perfect orientation. And finally, Part 5, a bit-perfect, hyperdeflationary future. Let's pivot for a second to the massive real-world macroeconomic and energy impacts of this paradigm shift. Because fixing the math doesn't just give us accountability, it fundamentally rewrites the economics of compute. Check out this number. 0.05 picojoules. That is the staggering, hard, absolute physical energy floor we unlock per operation when we transition to this new 1-bit LLM orientation using side-A normalization. To put that 0.05 picojoules into perspective, a standard 16-bit fluid operation, the kind full of complex, lossy approximations processed by the FPU, burns about 3.70 picojoules of energy. By replacing trig with exact bit shifts on the ALU surveyor, we trigger a massive 74 times reduction in energy burn. Eliminating the FPU gambler doesn't just grant us forensic digital truth, it ushers in an era of absolute hyperdeflation for global compute costs. We are metabolically optimizing the absolute core foundation of artificial intelligence. Which brings us to the end of our digital autopsy. And I want to leave you with a final provocative thought. By anchoring our math to 80 equals 1 and turning those messy quantum curves into exact straight lines on the ALU surveyor, we have completely bypassed the physical hardware crisis rotting the foundations of AI. We have literally cured the invisible non-deterministic drift. So, now that we finally possess absolute mathematical truth, what are you going to program it to do? Thanks so much for joining me on this explainer. Keep questioning the systems around you, and I will catch you next time.